After the define phase, which creates among other things a problem statement, we enter the measure phase to make additional measurements to quantify the problem. In other words, the data from the define phase is validated using specific tools. Introduction. The measure phase quantifies, qualifies, and validates the Six Sigma needs. These include the need for a problem, a process, a benefit, and a goal. In this phase, the project team discovers more opportunities and lays a foundation for the existing organization culture to follow. It is inherent in the project that there are going to be modifications and changes in the larger interests of the organization. In the measure phase, the project team is very likely to meet cultural resistance. Of course, in no organization it could be expected that the existing culture would immediately and warmly welcome a project that is going to attack the core practices and redefine measures of success. People's concerns will rise as during the measure phase, defects will be brought out in every corner and at the maximum scale, especially in the vital few crucial areas. But the project team's mandate is to find the real levels of defects, so that opportunities for improvement start unfolding at every level. The team members will have to redefine the problem to reflect the defects and also the true cost of the adverse effects. Objectives. The primary purpose of the measure phase is to focus the improvement effort by gathering information about the current state of the process. The purpose of the measure phase is sixfold. 1. To define or more CTQ characteristics. 2. To map the process in detail. 3. To evaluate the measurement systems. 4. To assess the current level of process performance, to establish a baseline capability. 5. To establish the short and long-term process Sigma capabilities. 6. To quantify the problem. The most important tools used by the project team in the measure phase include 1. Process mapping. 2. YX diagram. 3. Failure modes and effects analysis or FME analysis. 4. Measurement system analysis or MSA. 5. Capability analysis. The usual sequence of using the tools is process map followed by YX diagram and FME analysis. MSA tools are used to ensure that the data is appropriate for its intended use and is used to assess the measurement error. Usually, the MSA precedes capability analysis. What is process mapping? Process map is one of the most important tools the black belts use in the measure phase. A process map shows in detail the working of a process at various levels and in various stages. A number of techniques are used for process mapping. One of the usual ways is to use the flowcharting software. However, the project team may use PowerPoint, which is far more accurate and effective. A process map may comprise flowcharts of the steps in a process, such as operations, decision points, delays, movements, handoffs, rework loops, and controls or inspections. Process maps are living documents and have to be modified, updated, or created anew if the process is modified, updated, or changed. It is important to remember that the team might not find some of the data required for a detailed process map at the start of the measure phase. However, it is necessary to document the data that is available to know the extent and types of data required, because this categorization will help the team as it moves into analyze phase. The team should collect data that is essential to the project. Process mapping in detail is done as the team learns more about the progress along the course. Interaction with members and stakeholders is necessary to mapping. Newer and newer information takes the data and analysis to a level higher than what the team created in the defined phase. With richer information, the team can determine the right areas to focus its efforts to know more about the process. Process mapping symbol. In flowcharting, the 4 key signs to be used are oval, rectangle, diamond, and arrow. Start point is the point at which an input from a previous process supplier is received. Stop point is the point at which an interim product or service is delivered to the next process customer. Symbol, circle, and triangle are generally optional in flowcharting. They come handy when the process map is used as a perpetual documentation tool. In process management, it is necessary that every rectangle has at least 1 arrow coming in and 1 arrow going out. Incoming arrows represent the introduction of resources into the process, while outgoing arrows represent process deliverables for that activity.
Process maps should identify forms of waste. Flows of processes are interrupted by decisions points or places where the process can flow in 2 or more directions. The diamond symbol represents decision points and hence signifies waste. In all, there are 7 types of waste. In a manufacturing environment, the 7 elements of waste are easy to grasp. Making the connections in a service environment is more difficult. The waste of correction included the waste of handling and fixing mistakes. The waste of processing can be described as overprocessing, which does not add value to the customer. To cite an instance, in a transactional environment, too many levels of sanction and approval that delays issue of order. The team has to lay its finger on the problem where managers and employees spend a long time in their own mistaken belief that it should be detailed and perfect. Then, there is the issue of waste of conveyance, which occurs in the course of materials movement. In a manufacturing environment, it is very clear that the customer will not have to pay any extra money for materials that travels long distances. In the transactional setting, instead of materials, the conveyance deals with information. Information is acquired from a customer, manipulated or transformed, and then returned to the customer in a desired value-added format. Another type of waste is waste of motion. This type of waste relates to the movement of people to ensure value addition. In a manufacturing setting, this is closely related to ergonomics and workstation layout. Then comes 3 more types of waste: waste of waiting, waste of overproduction, and waste of inventory. These 3 types of waste come as the consequences of 4 types of waste discussed above. Waste in these 3 categories is an insurance policy that the process owners purchase in order to compensate for problems in the way the process flows.
Waste of waiting is defined as the cost of an idle resource. In both manufacturing and transactional settings, such waste is a consequence either of a bottleneck in the process upstream or defects in capacity planning and utilization. Waste of overproduction can be understood as excessive accumulation of work in process. For example, WIP, or finished goods inventory, which use a lot of organizational resources. Waste of overproduction is easy to quantify in manufacturing environments, but in a transactional setting, even though there might be significant stocks of WIP due to failures in the process flow, there are no finished goods. This is because services are not stored in inventory. They are delivered as soon as they are produced and finished. Must know for process mapping. There are several questions which need to be asked while drawing up process maps. For instance, who are the customers of the process? Who performs each activity? What forms and reports are used? What computer systems and files are used? What decisions are made in the process? Who reviews the decision and when? What is the nature, frequency, and cost of errors or problems? How are errors, problems, and exceptions handled? What is the output and where does the output go? There are also certain basics which should be known for any process. For instance, the key objective of the process, the key activities of the process, the main sources of data input for each activity, the key deliverables for each activity, recipients of the outputs of each activity, key performance indicators or KPI for the process, key volumes related to an activity. Do and don'ts for process mapping. Let's talk about what must be done. Map the process as it actually happens. Think about the process across the entire organization. Talk to the other people who are involved in the process. Define the beginning and end of the process before you start. Draw the process map at high level. Continue to ask questions. Now, the don'ts. Don't map process as you think it happens, or as you think it happens, or as you think it ought to happen. Don't restrict your process map to the activities in your own department. Don't get bogged down with too much detail. Don't struggle on your own. YX matrix. A YX matrix, also known as a cause and effect diagram, or a fishbone diagram, is a technique used to quantify and prioritize the nature and depth of the relationships between the input variables, or X, and the output variables, or Y. The YX matrix is very similar in function and structure to project prioritization matrix, as creating this tool deals with specific circumstances of many functions. The team for this purpose has to be cross-functional. The first step is entering the Y or outputs deemed important by the customer and the team. Score each Y between 1 and 10, with 1 being the lowest importance and 10 being the highest importance. Enter all the potential X that can impact the Y. This should be a full list. The team must now, through brainstorming, score the impact of each X on each Y. This scoring step may be very time-consuming and complex. It is necessary to emphasize here that a YX matrix is only a quantification of aspects that are most important in the team perception. As this quantification is not based on hard data, it is required that results are not accepted as true but treated with skepticism until verified for logic. The purpose of the YX diagram is to challenge the current beliefs and hence is expected to attract disagreements which should be dealt with in the healthy manner. Failure modes and defects analysis, or FME analysis. One of the standard techniques used to go further is a failure modes and defects analysis. The team uses this method to examine all possible problems in a process, the potential impact of each problem, and ways of dealing with each problem. FME analysis seeks answer to a primary question. For example, what does the team want to know about defect? This leads to detailed and deeper knowledge about the product, process, or service. Using this tool, the team focuses on collecting the information in a systematic manner and in a specific format. At the outset, FME analysis does not have anything more than the oral information based on the experience of people associated with the process. In addition, it may have the identified defects and the current data gathered. It is important to remember here that FME analysis is not a tool to resolve the factors that cause errors. It is a useful tool to identify potential factors and prioritize the order in which the evaluation of the factors should be done. Ideally, FME analysis should focus on the part of the process that has the highest scoring X variables from the YX matrix. It is necessary to remember 3 points here. 1. Each step can have several failure modes. 2. Each failure mode can have several causes. And 3. Each cause of a given failure mode can have a unique effect with various levels of severity. To conduct a FME analysis, one needs to calculate the RPN, or risk priority number. This is calculated after multiplying 3 things: severity rating, occurrence rating, and detection rating. Each of these is rated on a scale of 1 to 10. Rules for using the FME analysis. Some practical rules for using the FME analysis. An RPN greater than 80 is an indicator of a critical need for immediate action. A severity rating of greater than 5 indicates a safety-related defect. A high RPN with a low detection indicator is likely to result in defects escaping internal tests and reaching customers. A high occurrence rating is an indicator of poor process care. Degree of severity, or severity rating, is an indicator from 1 to 10, which indicates the seriousness of the failure mode. As an example, a severity rating of 1 indicates that the customer will not notice the defect, whereas a rating of 7 or 8 will result in high levels of dissatisfaction among customers, and a rating of 9 or 10 can endanger the customer. Occurrence rating is an indicator on a scale of 1 to 10, which indicates the probability that the failure mode will occur. For instance, an occurrence rating of 1 indicates that likelihood is remote, whereas a rating of 9 or 10 indicates imminent or certain failure. Detection rating is an indicator on a scale of 1 to 10, which monitors the ability of the organization to find and control the failure mode. As an example, the detection rating of 1 indicates that the potential failure will surely be found, whereas a rating of 9 or 10 indicates that the failure would not be found. Example of FME analysis. The example of service at a hotel and functions covered include service desk, guest support, food service, and medical service. Potential failure modes are provided, as are the severity, occurrence, and detection ratings. Potential causes of failure and current process controls are also highlighted. The RPN and recommended action is also provided. Measurement System Analysis. A measurement system analysis, or MSA, helps the team in making proper and effective measurements. It is a common experience that a measurement of the results of a process at any point of time will reveal some variation. The variation can be attributed to reasons. First, variation are natural in any process. Secondly, no method of measurement is perfect. It is for the project team to judge whether the variation is in the process or is owing to the imperfection of the measurement system. In case the variation is owing to the process, the team has to apply statistical process control to identify the sources and minimize the variation. In case the variation is owing to the measurement system, the team should judge the extent to which the variation can be attributed to the gauge, operator, or some other source. There are 2 types of measurement system errors: accuracy and precision. Accuracy refers to the difference between recorded measurements and the actual value of the parts measured. Precision refers to the variation in measurements
When a device is used to measure the same part repeatedly, errors of either type can occur within a given measurement system. A device can measure parts very precisely but do not accurately, or very accurately but do not precisely. A device may not be either accurate or precise. Let us assume a person has a dozen darts to toss at a dartboard. If the darts tossed end up clustered together away from the center, the tosses will be described as precise, but not accurate. If the darts all end up scattered around the center, the tosses can be said to be accurate, but not precise. If they all end up crowded at the center, then the tosses are both precise and accurate. If they all end up scattered all over the board and maybe onto the wall, the tosses are neither precise nor accurate. The above example gives simplistic view of the concepts of precision and accuracy. In practice, they are far more complex. Gauge R&R, or gauge repeatability and reproducibility, is a measurement systems analysis technique. Gauge R&R measures the amount of variability induced in measurements that comes from the measurement system itself and compares it to the total variability observed to determine the viability of the measurement system. The evaluation of a measurement system is not limited to gauges, but to all types of measuring instruments and test methods. Data collection plan. Precision in measurement system comprises elements, repeatability, and reproducibility. Repeatability is defined as variation due to the measuring device, when the same operator measures the same part with the same device repeatedly. Reproducibility is defined as variation due to the measurement system. It is the variation observed when different operators measure same parts using the same device. The team can perform the gauge R&R study on both attribute-based and variable-based measurement systems. Attributes data can be defined as data that fit into the categories that can be described in terms such as good or bad, go or no-go, pass or fail, correct or incorrect, and yes or no. Attribute studies are common to transaction settings. For instance, an invoice can be created either correctly or incorrectly. This will help the team in evaluating consistency in measurement among operator, clerks, bookkeeper, and agents. In case inconsistency is found, the team decided that the measurement system needs to be improved. Variable data can be defined as quantitative data. It is classed in categories, discrete and continuous. Example: we are assuming operators 1 and 2. Each operator is taking trials. Every trial has 10 parts. Fill the entries in the colored portion and you will automatically get the output. In the next slide, the example is given. Guidelines for acceptable results as follows. Less than 10% is satisfactory. 10% to 30% may be satisfactory. It depends on the magnitude of use, cost of new gauges, cost of repairs, etc. Greater than 30% is usually not satisfactory and requires corrective action, as is evident in the example. Total variation is 8.7%, which is satisfactory. Process capability. Process capability is assessed by the team to judge whether a process, which has short-term variations, has any potential long-term capability to meet established customer requirements or specifications. We need to understand the distinction between short-term and long-term capability. Short-term capability is undertaken over a short period of time, say days or weeks, and comprises 30 to 50 data points. This technique takes into account only the variations within a subgroup and excludes the variations across subgroups. In contrast, long-term capability is carried out over a long period of time, say weeks or months, and comprises 100 to 200 data points. It is aimed to measure actual long-term capability of the process. This study takes into account variations both within and between subgroups. CP and CPK are the most widely used indices of capability. CPK can be described as process performance and CP as process capability. CP is a ratio of the tolerance width to the short-term spread of the process. It estimates the instantaneous capability of the process. CPK is a measure of capability of a process to meet established customers' requirements, given short-term variation. It is a ratio of distance measured between process mean and specifications limit closer to half of the total process spread. Capability Index, CP. Tolerance width is the distance between the upper specification limit, or USL, and the lower specification limit, or LSL. Short-term process spread represents 6 times the short-term standard deviation, or plus minus 3 sigma. CP is based on several assumptions and is used for continuous data. The basic assumption in CP is that the process is statistically stable and that the data are approximately normally distributed. Because CP does not provide for process centering, the team cannot define process performance merely on the basis of it alone. What do CP results mean? If CP is less than 1, it implies process output are out of line with specifications that the process is incapable. If CP is equal to 1, it implies that the process barely meets specifications. There is a probability that at least 0.3% defects will be produced, and even more if the process is not cantered. If CP is greater than 1, it implies that the process output falls within specifications, but defects might be produced if process is not cantered on target value. CP equals to 2 represents short-term objective for process capability. It implies that the process is working with 6 sigma capability. Indices of capability. CPK constitutes a measure of process capability to meet established customers' requirements or specifications. CPK is a ratio of the distance measured between the process mean and the specification, divided by tolerance limit closer to half of the total process spread. CPK signifies the level of performance that a process can achieve considering the location of the process mean. It is equal to the smaller of either CPL or CPU. CPL is the process capability index using the lower specification limit. CPU is the process capability index using the upper specification limit when the process is centered. CPU equals CPL equals CPK equals CP. CPK is used for continuous data and is based on several assumptions. Key assumption is that the process is statistically stable, and another key assumption is that its data is approximately distributed. In case of the distribution of the data being much skewed, CPK considers process centering. Sometimes the data turns out to be non-normal. It is not unusual because no characteristic will produce a distribution that is exactly normal. The team should transform the data in this case. Transformation makes non-normal data resemble normal data. The team can use any of the data transformation tools that can transform the data. What do CPK results mean? If CPK is equal to CP, it implies process mean is on target. If CPK equals to 0, it implies process mean falls on the specification limits. Therefore, 50% of the process output falls beyond specification limits. If CPK is less than -1, It implies process mean is completely out of the specification limits. Therefore, 100% of the process output is out of the specification limits. Measure phase gate review. We have arrived at the conclusion of the measure phase. It is time now to hold a phase gate review. The black belt presents a detailed report to the executive team on the status of the project. With reference to the report, the executive team may raise queries, make critical observations, discuss ways to overcome hurdles, allocate resources where needed, provide reinforcement to the project team, and ensure that the project is on the right course. Phase gate reviews are not technical. It is assumed that the master black belt and the black belt have worked out any technical problems. They are primarily to ensure that the project is proceeding according to plan, that the team is meeting the deliverables by the milestones, and that the project is on time and within budget. Module test of failure modes and effects analysis, FMEA, describes which of the following: A. Potential defects. B. The risk of the problem. C. Capability of the process. D. Root cause. E. What you want to know about the type of defect. In an FMEA, what is the RPN if occurrence indicator is 5, detection indicator is 4, and the severity indicator is 9? A. 0. B. 20. C. 9. D. 180. E. None of the above. Measurement System Analysis, MSA, is used: A. To assess capability. B. To validate the data used for analysis. C. As an option tool during the DMAIC process. D. A non-statistical assessment of the process. Capital Logistics Case. Refer back to the previous CAPS Logistics case. For an output indicator which is timely delivery as per schedule, what can be 4 potential output measures? Also, rate the relationship for each of the output measures as strong, moderate, or weak. For instance, on time, yes or no, can be a potential output measure which will have a strong relationship. Can you think of the others? Assignment 1. For the CAPS logistic case, fill in the blanks for the high-level voice of customer, or VOC. Assignment 2. Spend 15 minutes drafting a process map for sending a fax. Draw the process map on a piece of paper using a pencil. Identify the start point and end point of the process. Remember to identify all the activities, inputs, and outputs. Use appropriate symbols while drawing the process map. Assignment 3. Given below is the YX matrix. Fill in the ranking and identify the vital few factors. Answer for the CAPS Logistics assignment. Operational definition of process to be measured. Process starts when a store order is received by Capital and ends when the order is received and signed for at the customer's dock. How will the process be measured? Deviation from scheduled delivery time measured in minutes. Specification limits, for example, USL and LSL. LSL equals negative 60 minutes. USL equals plus 60 minutes. Target is scheduled time or 0-minute deviation. Defect is delivery beyond plus or minus 60 minutes. Number of defect opportunities per unit is 1 opportunity for defect per scheduled delivery or freight. This is the end of our second module. Next module we are going is Module 4, Six Sigma Analyze Phase.